Okay, so this is what your graph should look like that you all graphed on the Elmo. If you have some points that are off, it's okay. Just go ahead and erase and fix them, please. All right, so this graph represents the cost of producing a can that will hold about 365 ounces based on the radius. And so we're actually going to find the equation for this graph, and then we're going to find the minimum cost. So it looks like a can with a radius somewhere between 2 and 3 would be the cheapest can to produce. So we're going to figure that out. So to start, we're going to make our equation for that curve. So the curve is the cost of the can. Based on the radius. So we have to start off with the cost of the can based on the radius and the height, and then we'll get it down to what we want it. So we would do the cost of the circular bases times the area of those. So those are both circles, so it's pi r squared, but since there are 2, we would do 2 pi r squared. All right, and then the sides, the cost of the side material times the area. Right. Now, the only thing that's wrong with this equation is that we have 2 variables and we only want one, and we want that variable to be r, because that was what the independent variable was in our graph. So I think you guys probably already figured out to find h, you would take the volume and divide it by pi r squared. And since our volume on this can is always about 365, that's what we could use to represent h. And then we'll go back and plug that into our equation on A. And we're going to call that C of R because R is going to be our only variable. So I will go ahead and multiply the 0.0005 by 2. Okay. And then the other one, I'm going to hold off on that decimal, multiplying it, and go ahead and plug in our fraction we just got for h. All right, so we do get the pi to cancel out, and then one of the r's will cancel out. So now I just need to multiply the decimal times 2 times 365. Now, I am completely fine with you guys using your graphing calculator to crunch numbers on this assignment in this lesson, because the calculus is hard enough on your own without trying to do all of these little multiplications without a calculator. So feel free to use calculators to do multiplications of decimals and stuff. I don't want you to use it to do the calculus stuff, like the derivatives or actually finding the max and min. We want to use calculus to do that. So anyway, this is the equation of those points. All right, so we need to figure out the least expensive can. So we want a basically relative minimum of this. And so we're going to use the first derivative test to find our minimum. So we will first find the derivative. All right, so this first one, we're going to do the power rule. We'll multiply by 2 and take 1 away. Now, it seems like on this lesson, there's a ton of these where you have a number over R or a number over X or a number over H or L or whatever. And so we can rewrite this if we wanted to as 0.168 R to the negative 1, multiply by the negative, take 1 away, and what it does is it moves that down to the denominator. But it's going to do that every time. So if we can see that pattern, it will save us tons of time. So what happens when you're taking the derivative and you have a variable down in the denominator, it doesn't have a power, it's just a regular r, is the sign changes and then it becomes r to the second. Right, and we'll do some later. We'll actually find the derivative of that, and we'll keep talking about what happens. But that is, if you can do that, just remembering the pattern, that's going to save you so much time. Okay, so what we want from the first derivative is the critical number, so we want to know when it is 0. Okay, so I'll just move that over. Multiply by r squared. Okay, and then we're going to divide. Now be careful. When you're using your calculator, the graphing calculator, if you have to divide by 0.002 pi, you're going to need to put that in parentheses or do the alpha y equals fraction button. Because if you don't, it will only divide by the 0.002 and then it's going to multiply about the pi. And so it definitely give you the wrong answer. So if you type it in correctly, you should get 18.589. And then we'll do the cube root. So to get the cube root on the graphing calculator, you probably haven't done that too much. You're going to hit math. And I don't know what number it is. It's around 4, 5. I don't know, but you can tell it's the cube root. And so the cube root is approximately 2.649. Now, we've seen the graph, and so we're pretty sure that that definitely is the minimum value for the radius, but we don't know for sure. We can make sure we know by doing the first derivative test. All right, and so we would plug in a value on the left side and plug in a value on the right side of your critical number and just make sure it does create a minimum. And so we are plugging those into the derivative. And so when you plug in 2, you are going to get a negative. And when you plug 3 into the derivative, you're going to get a positive. All right. And then when the first derivative changes from negative to positive, it does create a relative minimum. So that's how we know. So the radius that would produce the lowest cost is going to be a radius of 2.649 centimeters. Okay. And then if we want to know the height of the least expensive can, we can just take that and plug it into our height formula we were using earlier. All right. And that's going to give us a height of approximately 16.557 centimeters. All right. And then what is the absolute lowest price we can produce a can of LaCroix? So we can plug everything in. It doesn't really matter if we wanted to use the height and the radius. We could go back to that one. If we just wanted to use the radius, we could use C of R. That's what I'm going to do. All right, so that's going to give us a price of about 0.066 cents or dollars, or a little bit more than 6 cents per can. And that should be smaller than any of the prices you guys got, but it's really close to what you would get for 2 and 3. All right, so that is the process of optimization. So we'll just kind of break it down a little bit more. So some important ideas about optimization. What we're doing is we're finding a max or min in applied contexts. So this is a good one for people who like applied mathematics, not just abstract mathematics like we do a lot. So hopefully Montana will stay awake through these lessons. So the first thing that we're going to do is write an equation for the quantity to be maximized or minimized. All right, then, and that's what we did like on the number 4. All right, and then we have to use the constraints to find relationships between 2 variables. And sometimes you don't have to do that. Sometimes like your equation will already only have 1 variable, but in a lot of these you have to, maybe 3 variables you have to get down. So that's why you use the constraints. And then step 3, you're going to rewrite your equation with only 1 variable. Now, I do know there are some that you're given the equation that you need to maximize, so you can kind of skip down to number 4. All right, and then we're going to use the first and second derivative tests. Now, when I first started teaching this, I kind of focused on the first derivative test, like we did on this one, where you figure out if your signs change from positive to negative. But on a whole lot of these, the second derivative test is so much faster. Like you can find the second derivative super quick and then just know from there. But you guys can choose whichever one you like better. But on a lot of my examples, I just go ahead and do the second derivative test. All right, so on example 1, we're going to find 2 positive numbers, a and b, that minimizes the sum of twice a and b if the product of the 2 numbers is 288. So that is somewhat overwhelming when you read it. So what I always do is just focus first on what it says we're minimizing or maximizing. So we want to minimize the sum of twice a and b. So that's our equation we want to write. For the can problem, we were minimizing the cost. So we wrote an equation about cost. So that's your first step. Focus on what you're minimizing or maximizing. So since this is sum, I'm just going to call it S. So twice a and b. All right. Then we write our constraints. So the constraints are kind of secondary information that you're given, and that's the second part of the sentence. So we have to write these numbers. So the product of the 2 numbers is 288. So AB is 288, right? And then we're going to use the constraints to rewrite our equation with only A or only B. And that's up to you, whichever one you want to do. Typically, it doesn't matter. If one of them is being squared, I would have that be the variable you keep and the other one be the one you get rid of. But in the end, it ends up not mattering a ton. But I'm just going to just go ahead and solve this one for A. Then we'll go back and rewrite our equation with only 1 variable. So in the place of A, I'm going to rewrite it as 288 over B. This one might have been easier to do the other way, but it's fine. We're using a calculator. 2 times 288 is 576. Okay, now we're going to use the first derivative and the second derivative. So let's find the first derivative. I can just do it down here. All right, so this is another one like what we were talking about before. You have a number on the numerator and just a single variable in the denominator. So all we do is we're going to change the sign when we find the derivative, and then down there it becomes b squared. And then the derivative of b is just 1. All right, now what we want from this is a critical number. So we would take it and we would set it equal to 0. And we'll take the square root. This is a square root. You may not know, but the square root of 576 is 24. Okay, so right now, we don't really know if this is a maximum or a minimum. We just know this optimizes this one or the other. It's relative max or min, possibly. So what we want to do is figure out which it is. So I'm going to do the second derivative test. So I'm going to go and find the derivative of this one. This is a little different because it is a number in the numerator, but the denominator has a power. So this time we multiply by that power. And we do change the sign. So since it was negative, we change it to positive. And then it becomes b cubed on the bottom. All right, and then the derivative of 1 is 0. All right, so what we want to do, since 24 is a critical number, we can use it in the second derivative test, where all I need to know is when I plug in 24, do I get a positive value or a negative value? Well, everything is positive there. So a positive divided by a positive is positive. And the second derivative test tells you if you have a critical number and then you plug it into the second derivative, if you get a positive, it creates or it confirms a relative minimum, because that's concave up. Concave up at a critical number is the minimum. All right, so we're good on minimum. And we want to know that, so this is definitely B. So we want to know A. So to find A, I'll just take 288 and divide it by the B value. So A should be 12. Okay, so we just did a whole optimization problem. Now, we do have varying levels of difficulty, so some of them may be a little more difficult than that. So the next two you might find could be more difficult. So on 2, we have 200 feet of fencing to enclose a rectangular field by your house. One side of the field borders a pond and does not require fencing. What is the area of the largest field you can enclose? So let's draw a little picture because that definitely helps. So the pond side, I'm going to do like water. All right, and then we'll have our fence.